Hello everyone, welcome to the Bettersize channel. My name is Zhibin Guo and I'm an application engineer. A state-of-the-art nanoparticle size and zeta potential analyzer, BeNano 180 Zeta Pro from Bettersize is now on the market, and this will be a detailed presentation about it. This talk is divided into 4 sections. First, 3 concepts: particle size, zeta potential, and molecular weight that are involved in the BeNano will be introduced briefly. Next, the important technologies will be introduced in detail. Then, an explanation of features and benefits will be given, including hardware, software, and accessories. Lastly, I'll talk about a few typical applications using this instrument. Before we dive into the product, let's get to know some fundamental concepts. The BeNano analyzer enables accurate measurements on particle size, zeta potential, and molecular weight of nanoparticles, using the technologies like DLS, ELS, and SLS respectively. You may wonder what these concepts are and why they are important. Please follow me with a walkthrough on the introduction to them. What is particle size? It is a physical property to indicate how small or large a particle is. The effective control of the particle size and size distribution of materials are of great significance in many fields to improve product quality. There are many instruments and methods for particle sizing, and dynamic light scattering (DLS) is one of the most popular means for characterizing submicron and nanomaterials. DLS has advantages including fast measurement, easy operation, and good repeatability, and thereby becomes one of the principal methods for nanoparticle measurement. What is the principle of DLS to derive particle size? It is based on the Brownian motion of dispersed particles. Brownian motion is the random motion of particles suspended in a fluid, resulting from thermal fluctuation of the solvent molecules. As we see, the larger the particle, the slower the Brownian motion will be. Therefore, the particle size, which is dH in this equation, is derived from the diffusion coefficient determined by DLS through the Stokes-Einstein equation. In terms of size, a frequently asked question I got from users is why there is size difference between SEM and DLS. Simply put, SEM is a number-weighted method, while DLS is an intensity-weighted method. That's to say, large particles give more weight by DLS, making the average size look larger than the one by SEM. Besides that, SEM determines the actual size of the particles, whereas DLS calculates the hydrodynamic size of the particle, which can cause a slight size difference as well. Okay, we are done with particle size. Zeta potential is another concept that we need to know. Particles usually carry charges on the surface in aqueous systems, surrounded by the quantum ions that form an inner stern layer and an outer shear layer. Zeta potential is defined as the electric potential at the interface of the shear layer. The sign of zeta potential tells whether the particles are positively or negatively charged, and the magnitude of it is a key indicator of the stability of the particle system. Regarding zeta potential, one of FAQs is which factor affects the zeta potential of nanoparticles. In general, the magnitude and the sign of zeta potential depend on the chemical composition on the particle surfaces, and also the environment in which particles are dissolved, such as pH, ionic strength, and formulation component. So, keep in mind that zeta potential refers to the electric potential for specific type of particles suspended in specific solution environment. It enables the stability comparison between particle systems from different environments, formulations, and manufacturing processes. Suspension system with higher zeta potential tends to be more stable and less likely to form aggregates, while lower zeta potential leads to flocculation, aggregation, and agglomeration of particles. Zeta potential is extensively applied in many industries, such as chemical engineering, pharmaceuticals, environmental protection, food science, and on and on. In addition to particle size and zeta potential, another parameter offered by BeNano is molecular weight, which is the weight of a given molecule, which is measured in daltons. Molecular weight is a significant characteristic of polymer for determining the mechanical, bulk, and solution properties of materials. The technology used to determine the molecular weight is called static light scattering. I will talk more about it in the next section. After introducing the fundamental concepts, let's move on to the section concerning the product, the BeNano 180 Zeta Pro. Since 2014, Bettersize starts the journey to build the optical system of the BT series nanoparticle analyzer. Year by year, novel technologies such as laser Doppler electrophoresis, phase analysis light scattering, backscattering detection have been established. Until now, the BeNano series is fully developed. It integrates many of the technologies that Bettersize R&D department has developed to fulfill nanoparticle measurements and cover applications as many as possible. The BeNano series includes 7 models so as to meet the specific practical demands of users. With respect to the model difference, please look up in the BeNano product brochure for more information. This presentation will focus on the fundamentals of 180 Zeta Pro, since it's the flagship model that showcases the very best that Bettersize can do. I'm going to explain the technologies employed by the BeNano 180 Zeta Pro in this section. The first one is dynamic light scattering, DLS, that measures the size of nanoparticles. How does DLS work? Briefly speaking, the scattering fluctuations of particles are detected and then converted into correlation functions. Then, by using DLS algorithms, the average size based on intensity, or known as the average size, is calculated. In the BeNano, a coherent laser beam illuminates the uniformly dispersed particles in the sample cell, which scatter in all directions. The scattering intensity fluctuates over time due to the continuous random walk of particles undergoing Brownian motions. The APD detector determines the number of photons in scatter light at 90 degrees or 173 degrees, and the processor computes the sample's autocorrelation function. The diffusion coefficient is then calculated and used to give the Z average size through the Stokes-Einstein equation. To recap, DLS is based on the fact that the intensity of the scattered light fluctuates over time. As shown in the figures, the Brownian motions of large particles are slow, the scattering intensity changes gradually, and the correlation function decays slowly. However, when the particles are small and experience the fast Brownian motion, the correlation function decays more rapidly. By analyzing the correlation functions, the BeNano gets the diffusion coefficient, and then the particle size. This is how the DLS derives from scattering signals to particle size. On the basis of DLS, a state-of-the-art technology has been developed and employed by the BeNano 180 Zeta Pro, which is called backscattering detection. Instead of the 90-degree detection, an advanced 173-degree detection with movable detection point is used through the backscattering optics. When the detection point is in the middle of the sample cell, compared with the 90-degree design, the scattering volume is so large that the detector receives many scattering signals from the particles and increases the sensitivity of the instrument. It has better detection ability for dilute samples, which have smaller sizes and weaker scattering effects. However, the detection is not suitable for samples with extremely high concentrations and very strong scattering effects. Even if the sample is barely detected, the result will deviate from the true value. When the detection point is at the edge of the sample cell, the detection point is fixed near the wall of the sample cell. The laser beam does not need to penetrate the sample, which can effectively avoid the multiple scattering effect of high concentration samples and ensure the accuracy and repeatability of the particle size results in the high concentration range. However, due to its optical design, the scattering volume is so small that impairs the sensitivity of the instrument, and therefore the instrument is not competent to measure small particles with scattering samples or very diluted samples under this condition. The BeNano comes up with a solution. The optimal detection position and laser intensity are determined intelligently for each specific sample according to its sample concentration, size, and scattering ability. By doing so, the BeNano achieves the highest measurement accuracy. Another important technology that I want to introduce is electrophoretic light scattering, ELS, which is used to measure the zeta potentials of particles suspended in solution. In an ELS measurement, a laser beam irradiates the sample where the scatter light is detected at a focal angle of 12 degrees. The sample solution or suspension is subjected to an electric field applied to both ends of the sample cell, resulting in the electrophoretic movement of the charged particles. As a consequence, the scatter light experiences a frequency shift compared to the incident light due to the Doppler effect. Based on ELS, a more sophisticated technology, phase analysis light scattering, pulse, has been further developed. It's used to analyze the bit signals by measuring the phase shift instead of the frequency shift. In a pulse measurement, an alternating electric field is applied to the sample to change the electrophoresis directions of charged particles. The slope between phase change in time is proportional to the frequency shift. Since the electrophoretic mobility is proportional to the frequency shift, according to the equation, zeta potential can be derived from the Henry's equation using the electrophoretic mobility. So, pulse can provide the parameters including average zeta potential, electrophoretic mobility, and conductivity. What are the advantages of pulse? It can reduce the influence of Brownian motion of particles on the results, thereby providing higher statistical accuracy. In various applications, pulse can effectively measure the zeta potential of particles with very slow electrophoretic mobility at a high short concentration. Another important technology of the BeNano that I want to mention is static light scattering. It measures the molecular weight of macromolecules and proteins dissolved in solutions. During the measurements, the instrument detects scattering intensity of particles in solutions at different concentrations. The software computes the Rayleigh ratios of samples at different concentrations and plots them against the concentration into a Debye plot. The molecular weight, MW, and the second virial coefficient, A2, are then calculated through the intercept and slope from the linear regression of the Debye plot. Okay, we have walked through the important technologies of the BeNano 180 Zeta Pro. A unique design of the multi-angle detection has been set up to detect the scattering intensity at different angles for size, zeta potential, and molecular weight measurements. High-performance components are displayed in this table with descriptions. But let's skip these technical stuffs and turn to what the users truly concern, which is how the BeNano 180 Zeta Pro benefits the users. Along with the crucial technologies, the BeNano gives us many parameters. Through DLS, you can get a z-average size and polydispersity index of your sample. The size distribution can be provided based on the intensity, number, volume, and surface area. Although intensity distribution is the primary result given by DLS, the BeNano software offers the options for users to change the intensity distribution to number, volume, and surface area distributions. In case the results comparison between instruments or technologies like SEM and TEM. With ELS, The average zeta potential and its distribution could be measured so as to evaluate the dispersion stability of your sample. With SLS, the BeNano provides users with the molecular weight and the second virial coefficient, the significant properties of macromolecules. Some advanced parameters you may need for your research are also provided by the BeNano, such as diffusion coefficient and solution viscosity. The features and benefits are divided into 3 parts in my talk, including hardware, software, and accessories. Please note that only a few features are mentioned here, given our time restrictions, and it is strongly recommended to refer to the detailed information in the BeNano product brochure, which has been released on the Bettersize website. The BeNano uses a solid-state laser source with the power of 50 mV, which can generate coherent laser beam with high power, excellent beam stability, long service life, and low maintenance cost. APD detector is used in the BeNano series. The detector significantly decides the sensitivity of the instrument. APD is a more advanced detector than PMT because its quantum efficiency is larger than 70%, which is a huge progress compared to PMT. There's no need for high voltage power supply in the measurement and effectively increase signal-noise ratios due to high sensitivity of the optical system. There is an important 173-degree optics in the BeNano 180 Zeta Pro to enable backscattering detection technology. A common question that people usually have when they are conducting measurements is that is 173-degree optics superior to 90-degree optics in terms of the size measurement? The simple answer will be yes, in the cases where high sensitivity and high concentration range is essential. When it comes to measurement sensitivity, the scattering volume of 173 degrees under the same optical bench is much larger than at 90 degrees, allowing more scatter light signals to be received and around 10 times more sensitive than at 90 degrees. So the 173-degree optics has higher sensitivity for very dilute or small particles. For highly concentrated or turbid samples, the backscattering allows the detection point to be moved to the edge of the sample cell, which not only enables signal collection but also minimizes multiple light scattering. As shown in this figure, when measuring concentrated size standards, the results obtained from the 173-degree are in much better agreement with the nominal values, compared with the results from the 90-degree detector. Temperature is an essential parameter for DLS measurement and has to be precisely controlled. Therefore, the BeNano offers adjustable temperature between -10 and 110 degrees to meet various measurement requirements. On the BeNano software, the user has set the target temperature of the sample and the equilibration time left for the sample to reach the target temperature. Regarding the temperature control system of the BeNano, one of FAQs is what are thermal stability studies and how do we perform them? Thermal stability is the ability of materials to resist heating. One of thermal stability studies is to investigate the particle size and zeta potential of the samples under different temperatures, which is essential in many applications. With the temperature control system and corresponding software function, the BeNano allows users to carry out thermal stability studies on either particle size or zeta potential. There is a function of program temperature change, which can be customized by users. For example, users can decide the start temperature, end temperature, and the interval of each temperature on their own. This feature benefits those who need to study the stability of protein formulations, and it is useful to stimulate real-time aging and manually speed up the aging processes. Now let's move on to the introduction of the software. Besides the user-friendly interface and different types of reports, the SOP, Standard Operating Procedure, is one of the highlights that allows the measurements independent of the operators. All essential parameters that measurements require will be input one by one with the help of SOP. For the DLS measurement, the research-level software offers the intelligent evaluation and processing of signal quality to eliminate the effect of random events. Results of Z-every particle size, distribution, and PDI can be obtained by different analysis models of the software. For the ELS measurement, the software uses the algorithm of pulse to provide the zeta potential and its distribution, with several built-in analysis models corresponding to different polarity systems. Another benefit of the BeNano is the versatility for accessories. For size measurement, there are 6 kinds of cuvettes. The disposable plastic cuvette is commonly used, within the temperature ranging from -10 to 70 degrees, and only for aqueous solvents. If your sample contains organic solvents, then the glass cuvette will be a wise choice. Depending on the solvent type, sample volume, and measurement temperature, a suitable cuvette is always available. For zeta potential measurement, the dip cell for organic solvents and folded capillary cell for aqueous solvents are available. The folded capillary cell provides excellent repeatability of zeta potential measurements. With the help of it, the instrument can provide a more uniform electric field and thereby more accurate results. It is only 4 milliliter thick and able to measure high concentration samples up to 40% weight per volume. It is disposable with low cost, therefore the sample cross-contamination could be avoided. It is easy to use when we are performing a measurement. Slowly add the sample from the syringe or dropper into the folded cell, and make sure that the amount of sample just immerses the electrodes, and then insert the cell into the sample holder. Following these steps, the sample preparation is finished for zeta potential measurement. For the size measurement of the BeNano, there's a cuvette designed for ultra-micro-volume sample, called it capillary sizing cell. Extremely low sample volume, down to 3 microliter is required. It can avoid large particle sedimentation, so microparticle measurement becomes possible. It has very small inner diameter, which is 1 millimeter, to avoid the effect of turbulence or convection on the signals. Another benefit of a small inner diameter is the low multiple light scattering effect that affects the size result. When you are performing a size measurement, just dip the sample and then put the cell into the supporting bracket. Adjust the height of the sizing tube until its upper end is aligned with the top of the bracket. Then put it in the sample holder of the instrument. That's it. The sample is ready for test. See, the sample preparation becomes very easy. In addition, the capillary sizing cell is disposable with low usage cost. After a brief introduction to the features and benefits, a few key applications with the BeNano series will be shown as examples, which is the last part of this talk. Lysosome is a commonly used enzyme. The simple structure and low cost make it a popular model in biological research. The molecular weight of lysosome is small, and the scattering intensity of lysosome is very weak. Therefore, measuring lysosome is always a challenge for DLS measurement. The BeNano was used to measure the particle size and molecular weight of lysosome in this application. As shown in the table, the particle size was measured to be around 4 nanometers. The molecular weight of lysosome was calculated through the Mark-Howick equation using the kappa and alpha constants of lysosome. It can be seen that the calculated molecular weight of lysosome at the concentration of 30 mg per milliliter was very close to the literature value, which is 14.5 kilodaltons of lysosome. The Z-average mean of lysosome was stable at various temperatures below 50 degrees, while they increased dramatically when temperature exceeded above 55 degrees due to a structural change caused by the denaturation of lysosome at high temperature and consequently the generation of a significant number of aggregates. As shown in the size distributions, the particle size of lysosome was initially small and had a narrow distribution at room temperature, whereas large lysosome aggregates were formed due to protein denaturation at high temperatures. In this application, SLS was used to characterize the molecular weight of a polyethylene oxide standard dissolved in water. PO aqueous solutions were prepared at different concentrations and then filtrated. The scattering intensity of PO solutions were detected with various concentrations. The Debye plot is then constructed by plotting and linearly fitting these values versus the concentration profiles of the suspensions. The slope of the linear regression equation is used to calculate the second virial coefficient, A2, while the extrapolation of the linear regression to zero concentration used the reciprocal of molecular weight. The deviation between the measured value and the literature value is around 10%. The results endorse the ability of BeNano for characterizing molecular weight. In this application, the particle sizes of two high-concentration pigment suspensions, red and yellow samples, were measured. Due to the high concentration and poor light transmittance of the sample, a capillary sizing cell with an inner diameter of 1 mm was used for the DLS measurement. Although both pigment samples were nanometer sized, the yellow pigment sample had a larger particle size, but a narrower size distribution than the red pigment sample. The particle size difference had been discerned accurately. Studies on micelle self-assembly can be carried out using the BeNano. In this application, particle sizes of two micelles, Twin20 and SDS, were measured. As shown in the table, on the one hand, the Z-average values of Twin20 were relatively stable upon changes in temperatures as well as concentrations. On the other hand, for SDS surfactant micelles, the particle size highly depends on its concentration. At a concentration of 25 mg per milliliter, in addition to the formation of several nanometer-sized micelles, large aggregates of several hundred nanometers also formed. When the concentration increased to 50, the amount of large micelle aggregates decreased significantly. Regarding the temperature trend measurement of the BeNano, I would like to give an example. Nippon is a thermosensitive polymer which has been studied since the 1990s. It shows a phase transition due to temperature variation. When the temperature axis is low critical solution temperature, around 32 Celsius degrees, the polymer chains gradually shrink to be a collapsed conformation because of hydrogen bond interaction and hydrophobic effect. The phase transition behavior is reversible. In this application, we characterize the sizes and zeta potentials of a Nippon hydrogel with the change of temperature and study the impact of solution environment on its structure. During the temperature raising process, the particle size of Nippon hydrogel decreases when temperature increases, while the count rate gradually increases. When it eventually reaches 50 Celsius degrees, the particle size is reduced to around 350 nanometers. Obvious high hysteresis of the phase transition can be observed in the heating and cooling cycle. It is because Nippon needs to absorb energy in order to form the hydrogen bonds upon heating, while the cooling process is attributed to the released energy from the breaking of hydrogen bonds. The zeta potentials of Nippon hydrogel are negative in the detected temperature range, which means the sample carries negative charges on the surface, and the magnitude of zeta potentials increases with the elevation of temperature. When the temperature reaches 50 degrees, the potential is increased to around -24 millivolts. In summary, the decrease of particle size leads to the increase of surface charge density, and zeta potential reflects the degree of charge density. BSA is a protein purified from bovine blood. Because of its spherical structure and low cost, it is a model protein in industry and scientific research. It has very weak scattering due to its low molecular weight and is hard to detect for light scattering measurements. In this application, 3 measurements of the BeNano were performed. As shown in this table, the zeta potential value of BSA sample in an aqueous solution was negative, indicating that the BSA particles were negatively charged in the current environment. For the particle size, a thermostability study was carried out. As a protein, BSA is sensitive to acid, alkali, temperature, and other stimuli. Its structure will change at the high temperature, and its biological, physical, and chemical properties will also respond to changes. And in many cases, these changes are not reversible. As shown in this figure, particle size increased significantly when the measurement temperature reached 65 degrees or higher, indicating that the BSA denatured at high temperature and formed large aggregates. In addition, we have investigated the changes of molecular weight of BSA upon the different aqueous environments. A Debye plot was constructed and the slope was calculated to provide molecular weight. According to our knowledge, when BSA was dissolved in aqueous environments, they form oligomers and aggregates. Therefore, the actual molecular weight will be larger than that of the BSA monomer, which is 67 kilodaltons, and this fact was endorsed by the measurement results. In conclusion, 3 important properties of proteins were measured using the 3 techniques with only 1 instrument. That's what the BeNano 180 Zeta Pro can offer. Finally, here are summaries. In this talk, I gave the introduction to the fundamental concepts, important technologies, features and benefits, and key applications of the BeNano 180 Zeta Pro. Okay, this is the end. I hope you find this video helpful. Please do not forget to subscribe to our channel. For more information, feel free to visit our website. Thank you for watching. Bye!